In particular, we are checking out the first question of the FRQ section. So for our first question over here, it says we have a block of mass M and it's released at rest at point A height of 6r above the horizontal. After being released, the block slides down a track as shown. When released from point A, the block does not lose contact with the track at any point. Points B and C are located at the highest points of their respective loops, both of radius r. All frictional forces are negligible. So in my drawing, I went ahead and labeled a couple of the main things that they mentioned. Everything starts from rest. So as I'm taking a look at this question, it reminds me a lot of roller coaster concepts and obviously a lot of energy things as well. And if we have a V naught of 0 meters per second, we have no kinetic energy, all potential energy. And then I went ahead and marked the heights of spots B and C because we have half a radius going up and then another half to complete the diameter of that circle. And then the same thing over here, 2r for the actual circle with the additional 2r below it with a height of 4r for part C. And there's no friction, so we're not worried about any thermal energy or anything like that. It'll probably be clean transitions from gravitational potential energy to kinetic energy. Now, with that being said, here is our first question. It's asking us to draw in diagram B, basically coloring in the amount of gravitational potential energy and the amount of kinetic energy. And when I took a look at my first bar graph over here, I noticed that it went up 1, 2, 3, 4, 5, 6 dashes up the chart. So it was 6r, it was a 6r height, which means that each little dotted line would be representative of a single radius. Now at point B, we were at a height of 2r, so then obviously then I would go 2 dashed lines up to represent a height of 2r. And then because of the conservation of energy, I want to make sure I have basically 6 little blocks of energy total, which means that I go up 4 blocks for my kinetic energy to make sure the energy is conserved overall. All right, going down to our next one. B is definitely a little tougher. It says, starting with the conservation of energy, derive an expression for the speed, which is basically the velocity of a block at point B. Express your answers in terms of r and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. So I take a look at my formula sheet, and plus I already have this one in mind. Work equals delta E. We have no work, no external forces acting on our system here. And we have the final minus initial as our delta E, so which is basically the energy of position B minus the energy of position A, and then those can be set equal to each other to show that energy is conserved. Now at our first position, as I said before, it starts at rest, so we have 1/2 mv squared for the kinetic energy, which is 0 joules. And then for the gravitational potential energy, it's supposed to be mgh, and our first h is 6r. Now for our second location, it has a height of 2r. So instead of mg6r, I replace that with a 2r. And we are going to have some kinetic energy. So it's going to be 1/2 mv squared. But one of the masses got dropped anyways because there's an m in every expression here. So it's just 1/2 v squared for now. So all I did is subtract g times 2r from both sides, which after I minused or subtracted g2r from g6r, I got g4r equals 1/2 v squared. So multiplied both sides by 2, brought it up here, square rooted it, and then I got a final answer of square root of g times 8r. And then if you wanted to pull out the 2 in front, you could do that. I would guess that it wouldn't matter anyways. All right, going to the very last portion of this. It says, on the following dot that represents the block, draw and label the forces, not components, that are exerted on the block at the instant the block slides through point C. So point C is basically the top of a loop. So it's kind of like the top of a roller coaster. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So I immediately knew that there was going to be an FG because there's always a force of gravity down. And then because the block is at the top of the loop is pushing perpendicular downward. Now, the thing I was wondering though was which is larger, the FN or the FG? Now, the way they worded it, I'm guessing it actually doesn't matter because it doesn't have a special note about the relative lengths of the vectors. So this is all just kind of an FYI, nothing to really worry about though, as far as your scoring. So we know that these two, Fn and Fg, are going to be pointing towards the center of your circle because this is at the top of your loop. So these two would be pointing towards the center. Therefore, they are centripetal forces. So you can set that equal to mv squared over r. Now, long story short, v squared for point C is going to be G4R. The reason why it's G4R is because if you scroll up here, before we subtracted G2R, but then we'd actually be subtracting G4R for point C. So if we change this G2R to a G4R, then I would subtract 4R from 6R, which would leave G2R that I would multiply by 2, and then that would end up being G4R for my final answer. Now, it's the square root of G4R. So if you take V squared, it basically just removes the root, and then you have G4R. So then our R's cancel. Then we have Fn plus mg equals 4mg, and then that would be the normal force is 3mg, which means that my vector for Fn should be larger. But again, the question didn't specify and ask for the relative size of the vectors to be proportional to the amount of force. So I don't think they're going to be grading that. And then for our final one, it says a student claims that 4R is the minimum height of point A such that block can slide down through point C without losing contact with the track after the block is released from rest. Briefly explain why this claim is correct. So you want to make sure you pay attention to the key words. I don't particularly like explaining. I'd rather just write out some formulas and show it that way, but they were asking me to explain, so I'm going to go ahead and use my words the best I can. So I wrote the total amount of energy would be mg4r because the object starts at rest, so that's the total amount of energy. And then at point C, the height is 4r, so it has the same gravitational potential as point A, therefore there would be also have a velocity of 0 meters per second. So if it has no velocity at the very top, then it would kind of just fall off. So that would make it lose contact, and then bam, it's over. Everything's all correct. So hopefully you did well on that. Question number 2 of our FRQ section, which is the experimental design one, which has a lot of different parts. Some of them are a little tough. Overall, I don't think it was too bad. So let's go ahead and read what we got here. So a student hangs a spring of unknown spring constant K vertically by attaching one end to the stand as shown in figure 1. And we only have a variety of cylinders of unknown masses, a stopwatch, and a digital scale. Okay, so we don't have every single thing we need, so we have to be conscious about the things they provided. And then design an experimental procedure the student could use to determine the spring constant K of the spring. So we're looking for a procedure, and we want to have enough detail so another student could replicate the experiment. And then we want some steps necessary to reduce experimental uncertainty. So based on the things they gave us for the stopwatch, we're going to be looking for the period, the amount of time it takes to complete a cycle. So like start from the bottom, go all the way to the top, and then back down to the bottom. And then we have the symbol M, the mass of the cylinders. So here's what I'm going to do. This is probably not the perfect procedure, but I think it's pretty decent and then covers most of our bases. So we're going to measure and record the mass of each cylinder using the digital scale, hang a mass from the spring, allow it to hang at rest, pull the mass down, and then because we don't have any measurement tools like a ruler or a meter stick, I said about 3 centimeters the width of your thumb because I'm kind of pretending like I'm speaking to a student. And then release it. After 1 or 2 up and down cycles, hit start on the stopwatch at the lowest position and then hit stop after it has returned to that position 5 times. So I want to make sure it's 1 full cycle, which is the bottom all the way back to the bottom again. Divide your time by 5 and then record that as your T, your period, and repeat steps 1 through 5 for each mass. So I don't know if that's the perfect procedure or not, but that seems pretty decent to me. I may have forgotten some minor details, but that seems to be the gist of it. All right, now we want to indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. So we have to be thinking about the formula period of a spring equals 2 pi times the square root of m over k. In that case, if I see m over k, then I'm thinking the delta y over the delta x. So I'm going to want to put the vertical mass of m, mass on the vertical axis, and then the time squared on the horizontal. Because when I do some algebraic rearranging, I square everything, and then I have k equals 4 pi squared, and then I have m over t squared. So I'm going to want mass for my y-axis and t squared for my x-axis. And then I just basically explained it here. I said if you rearrange the period of the spring equation, then the product of 4 pi squared and m over t squared is k. So if you take the slope of m versus t squared, then you would find the value of m over t squared to be multiplied by 4 pi squared to get k. You can also switch what's on each of these axes, but then you would have to do 4 pi squared divided by your slope, and that would actually give you the same exact answer. So I'm guessing there's going to be multiple ways you can get the same answer. That's just the thing that came to me most naturally. Now we are continuing the experimental part of it, but it's going to be a different scenario, clearly. So we have a cart that is at rest. It's pulled outwards. It has a mass of 0.25 kilograms. We got a motion detector over here and a force sensor over here. So important things to remember: we release it from rest, it oscillates back and forth, and then that seems to be it. So we have a velocity versus time graph where I circled 2 points that we're going to use a little bit later, and then I shaded some areas over here and over here, which kind of faded a bit, but we're going to use those a little bit later as well. All right, so for part C, it says using the velocity versus time graph, calculate the change in kinetic energy of the cart from time equals 0.5 seconds to time equals 2 seconds. Show your steps and substitutions. So this one is pretty straightforward. I'm actually almost surprised how simple it is, but our delta K is the final minus initial, which is the kinetic at 2 seconds and 0.5 seconds. So at 2 seconds, it was 0, and at 0.5, it's 0.3 meters per second. So then I basically just plugged those in for my velocities, subtracted, and then you have a negative change in kinetic energy. For the second part, it says using the force time graph, estimate the change in momentum of the cart from 0.5 seconds to 2.5 seconds. Briefly explain how you arrived at your estimation. And it says estimate because the first thing I'm thinking of is change in momentum is impulse. And then when you do force times time, you're finding the impulse, which is the area between the curve and the x-axis. And since the line is curved, it's going to be hard to find that exact area. So from 0.5 to 2.5, I'm going to go ahead and look at it. So here's 0.5 to 2.5. Now I immediately notice that I have this portion underneath in the negative region, and then this portion over here that is basically the same thing in the positive region. So I'm already predicting that it's going to be about 0 because I'm going to have some negative value here that's going to match this positive value, and they're going to cancel each other out. So I'm just basically articulating that and then saying that the area between the curve and the x-axis is the impulse. The amount of area between 0.5 and 1.5 looks to be equal to the area between 1.5 to 2.5 seconds. Therefore, the delta P, or impulse, is about 0 kilogram meters per second, because from 0.5 to 1.5, that has a negative change in momentum, and 1.5 to 2.5 has a positive change in momentum. So that seems to be pretty clearly explained. Maybe not the best, but I think I got the point across. Now, do the data from the velocity versus time graph confirm your estimation from part C? Briefly explain. So I'm going to go ahead and look at the velocity from 0.5 to 2.5. So here's 0.5 to 2.5. So they're both at 0.3. So there is no change in velocity. So my delta P, my impulse, is mass times change in velocity. And if my change in velocity is 0, that means my impulse or change in momentum also has to be 0 because the mass doesn't change. And both velocities are 0.3, therefore the delta V is 0 meters per second. So maybe I need to add a little bit more there, but it did say briefly explain. And if there's no change in velocity, then there's no change in momentum in this particular case. And that does it for question number 2. Number 3. So we have a wall here with a string and a beam, and everything is all at rest. So it says the following rectangle represents the beam in figure 1. On the rectangle, draw and label the forces exerted on the beam. Draw each force as a distinct arrow starting on, pointing away from the point at which the force is exerted. So we basically have a few different things to make the net torque 0. We have the force of gravity located at the center of mass. We have the force of tension right along the actual line of where the string is. And then we have the force of the hinge that is slanted in the opposite direction of our FT, kind of helping with that upward force to counteract the FG. Next, I drew a little bit extra here on the picture, which we'll kind of discuss later. Actually, we'll go ahead and discuss that now. We have the string that was originally here dotted at space 1, and there was a certain amount of tension, and it has what I called an FT1Y and an FT1X. The FT1Y is the thing that's applying the counter torque to the force of gravity. And then as that angle is dropped down, we have a much smaller FTY component, a much smaller torque there. So it says we're looking at the string is attached to lower on the wall at point 2. The beam remains horizontal as shown in figure 2. The angle between the beam and the string is theta equals theta 2. The dashed line represents the string shown in figure 1. The magnitude of the tension in the string shown in figure 1 is Ft1. The magnitude of the tension in the string shown in figure 2 is Ft2. Indicate which of the following correctly compares Ft2 and Ft1. So Ft2 is definitely much bigger, and the reason being is because it had that much smaller vertical component due to its angle. The actual value of Ft has to be much higher. So I wrote the vertical component of Ft2 would be smaller, so the tension would have to increase to counter the torque from Fg. Now, starting with Newton's second law in rotational form, alpha equals the net torque over I. Derive an expression for the magnitude of the tension in the string. Express your answer in terms of m, theta, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. So we have alpha equals the net torque over I. We know that there is no alpha because there is no actual movement or rotation of any sort going on. So if 0 equals the net torque over I, multiply both sides by I, which basically drops it. So the net torque equals 0. So that means the torque from the force of gravity is going to be the same as the torque applied by the cable. So here's gravity. It's mg applied to the middle of our beam. That's why it's L over 2. And then our Ft, which is the cable itself, times the sine of theta to get that vertical component times L, because it's acting at the very end of the beam. So I scooted over the Ft sine theta L to the other side, basically rearranged it a little bit. I crossed out the L's cancel out, which leaves mg, and then 2. The 2 is basically in the denominator, and then divide both sides by sine of theta. So then the sine of theta joined the 2 in the denominator, and our Ft equals mg divided by 2 sine theta. Now next, is your derived equation in part C consistent with your justification in part B? Explain your reasoning. So yes, the sine of a smaller angle is a smaller value in the denominator, causing a greater Ft. So if we have a smaller angle in here, then this overall number in the denominator is smaller, and then the entire number itself for Ft is going to be larger. Now this one is pretty tricky here. I had to really think about this one. It says the string is cut and the beam begins to rotate about the hinge with negligible friction. On the following axes, sketch the angular speed of the beam as a function of time for the time interval while the beam falls, but before the beam becomes vertical. So I'm thinking to myself, of course, the angular speed has to increase It's not going to increase in a nice linear fashion. So do I want something that has an increasingly steeper slope or something that has a much more flatter slope towards the end? So I drew a little bit here, which isn't really necessary, but just kind of for you all to see conceptually that my mg, which is causing the torque, is basically acting how it applies torque to the beam, and the amount of torque that it provides is less and less, which means that the angular acceleration that it experiences is going to be less and less. So it's going to have more acceleration in the beginning, and then a little bit less and a little bit less. So then therefore we have a curve that starts up steep and then gets progressively flatter. And that's it for question number 3. Free response question number 4. So we have a pendulum here that's a small sphere, and I drew a little bit here. We have the force of gravity pulling straight down, and it's got a couple different components. This little component that's slanted, horizontal, or tangential to its path is the thing that's causing it to speed up, slow down, and the thing that is doing work on the pendulum. So it says, the pendulum is now taken to planet X. The mass of planet X is the same mass as Earth, but the radius of the planet X is greater than the radius of Earth. The sphere is again brought to point A, displays theta from the vertical, released from rest, and swings through its lowest point at point B. The work done on the sphere by planet X between points A and B is Wx. So I said over here that the force of gravity equals gmm over r squared. If the radius is larger, which is an inverse square relationship to Fg, then the Fg is less. And then the work is the parallel force times the distance. So the parallel force is a component of Fg. Therefore, the work of X has to be less than the work of E, the work done on Earth. On the next page, there's kind of a lot going on here. So let me go ahead and sum it up. We got a couple things going on. We have the same exact situation. The new string is slightly elastic, and the length of the string may increase or decrease depending on the tension applied to the string. And then mostly everything is the same. The new pendulum is then taken to a different planet, planet Y, where the radius of the planet Y is the same as the radius of Earth, but the mass of planet Y is larger than the mass of Earth. Now it's asking in a clear, coherent paragraph length response may contain drawings, explain how Ty could be larger than Te or also could be smaller than Te. Now, I'm not quite sure if I articulated this exactly the way that AP would have liked, but I broke it up into the could be smaller section, and this is the way I did it. The increased mass would increase the Fg and G. So I made like a little note over here if this mass increased. And then which would decrease the value of Ty because it basically gets more force. And then if this effect is greater than the effect of the elasticity increasing, the Ty, the period, then Ty would decrease. And then I show another thing here where the period of the pendulum is 2 pi, the square root of the length of the string, divided by G. And then if we had a larger G over here, then we'd have a smaller period. So I maybe could have added a little bit more detail, but that's the main idea involved in making the period smaller. Now, as far as making it larger, the elasticity would increase the pendulum's length, causing a decrease in the period. Actually, that's supposed to say increase. So causing an increase in the period. And this effect is greater than, well, definitely couldn't write on this one. So one than the effect of the increased Fg and G, then the Ty would be larger. So if we have 2 pi square root of L over G, if we increase this L over here, then we're going to increase the overall period if the effect of increasing this G doesn't basically counteract that one and nullify it completely. So it just depends on the effect of each one of them and the degree to which they affect it. But I think something along the lines of what I said follows the concepts that you would have to know or have to be able to articulate. The way I articulated them, especially with not writing some of the correct words, wasn't the greatest, but I think you get the idea. So hopefully you did well in that question. We're taking a look at free response question number 5, the very last one. And we have a block A sliding along a horizontal surface. And we have block B that's at rest. The blocks collide elastically at t equals 1 second. As a result, the magnitude of the change in kinetic energy of block B is 9 joules. All frictional forces are negligible. So I made a little note to myself that the change in kinetic energy for block B is 9 joules. And if it's an elastic collision, then the change in kinetic energy for block A is negative 9 joules. So determine the speed of block B immediately after the collision. So block B was initially at rest. So basically the 9 joules equals the kf, so 1/2 mv squared, which it comes out very nicely mathematically. 1/2 times 2 is just 1. So it's basically v squared equals 9 joules. Square root of 9 equals 3 meters per second. So hopefully that one was pretty simple for you. Now going to the second part, there's a lot more going on here. So it says, draw and label the 3 lines to represent positions of block A, B, and the center of mass of the 2-block system as functions of t between 1 and 2 seconds. Each line should be distinctly labeled. All right, so I'll tell you what I was thinking in each of these different parts. So let's start with block A. So block A has some kind of speed that we didn't know before. So I went ahead and found the slope of this line, which is pretty easy because it goes up 2 meters over 1 second. So it was 2 meters per second. So initially it had a kinetic energy of 1/2, mass of 6 kilograms, and that velocity I just found 2. And then I found we had an initial kinetic energy of 12 joules. As I said earlier, if the other one gained 9 joules, this one lost. So 12 minus 9 is 3. And then set that equal to 1/2 mv squared to solve for the new v, which came out to a nice even 1. So all I have to do is across the next 1 to 2 seconds have a slope of 1, which is just pretty simple. So just go up 1 meter in that 1 second, and then I end at the 3 meter position. Now, as far as as 3 goes, or not 3, B, it has a slope of 3, which we just solved for. So that one I was already prepared with. So it's only from 1 to 2 seconds, so up 3 over 1. So I went from 2 to 5 meters to have a slope of 3 meters per second. As for the center of mass, because the momentum is conserved, it would have continue with the same momentum before and after the collision. So the mass stayed consistent, which means the velocity has to stay consistent. So I had this little dotted slope that went from about 0.5 to 2. So about 1.5 meters in that 1 second. So I continue another 1.5 by going from 2 to about 3.5. And then I call that COM for the center of mass, the one in blue. Now it says, consider in the original scenario, instead of colliding elastically, the blocks collide and stuck together. Describe how the line drawn for the center of mass in part B would change, if at all. Briefly justify your response. So if they are colliding as an inelastic collision, there would be some differences, but it wouldn't change because the momentum is conserved if it's an elastic or inelastic collision. So similarly to the things I was just saying, if the mass is constant, then the velocity of the center of mass is as well. Therefore, the slope would remain the same. So like I said, just kind of recapping on the same things. Momentum is conserved, mass is the same, so velocity has to be the same, and the slope is representative of the velocity, so that means the same. And that is the end of the exam. So hopefully you did well on question number 5 and the test overall. Thank you very much for watching and listening.